morning, friends. Here I am again today for the course Aircraft Stability and Control. I am in lecture number 49 and tutorial number 9. Here I am discussing about pure pitching and dynamic stability. In our lecture class, we have discussed for our last classes about dynamic stability. We should know what is the stability. Stability of aircraft is the tendency of aircraft to come to its equilibrium position. When we talk about static stability is if you take the aircraft, this is the aircraft is flying, and due to some gust came from this side and it is nose has been up. If you remove this force, whether the tendency is coming to its equilibrium position or not, if it is there, then we can say that aircraft is statically stable. And if after disturbance, aircraft is going away from its equilibrium position, it is called divergence. If a aircraft is diverging from its initial condition, then we can say that aircraft is statically unstable. And when we disturb it and it got disturbed, and after disturbance, if the aircraft is maintaining the same condition, like it is going like this, there is a disturbance, it is disturbed and it is moving like this, then it is a neutral stable. So up to neutral stable, we can accept the aircraft for dynamic stability. When we talk about dynamic stability, a time factor is involved. After disturbance, it may go like this, it is a short time. And if it is going like this, then it is a long time. And for this, it is a longitudinal dynamic stable. And if it is going rolling, pitching and yawing, if all the things are happening, then it is a lateral and directional dynamic stability. But here the time factor is very important. Time should be given to undertake this problem. So today I am talking about pure pitching. Once I talk about pure pitching, means it is no other things are happening. Only if the disturbance is taking place, only nose will go up and down. No plunging will not be there. Means up and down. It is called the plunging. So if aircraft is going like this and it will do only like this, this is called the pure pitching. It will not go like this or like this, no other motion. So it is an ideal condition which we can simulate in wind tunnel. In the real flying, pure pitching is not possible. However, if we fix this thing inside the wind tunnel with the bearing in a y-axis, so aircraft can move in y-axis or longitudinal motion will take place. Only the pitching up or pitching down. There will not be any lift component or no other sidewise forces. We will be blocking it. So only one dimensional motion, and that is to only pitching motion will take place. So that is called the pure pitching, and it is as a approximation to solve the dynamic cases. So in this lecture, I will be discussing about pure pitching motion, then natural frequency and damping ratio in this case. Then I will go for the dynamic stability and the Routh criteria, how this Routh criteria can be implemented to find out the dynamic stability of the aircraft. Today, in this class, some of the very important questions we are going to handle. These questions to be answered in this lecture. These are the what is pure pitching? how the natural frequency and damping ratio calculated in pure pitching. Routh criteria. What is the Routh criteria and how this criteria can be implemented to find the dynamic stability of the aircraft? And after that, I will be taking a small numerical where these theories which we will be studying is used for that purpose. So, till now we have developed 6 degrees of equations of motion. We have used the Laplace transformation and the Routh criteria to assess the dynamic stability. What is more important from these equations of motion? Equations in longitudinal motion give short period and long period, that is called Phugoid mode, in which the kinetic energy is converted to potential energy and vice versa. In this class, I will be taking the case of pure pitching. So, in longitudinal motion, we can see that if the aircraft is flying in x direction, this is the positive x, in this direction, in positives or negative in the vertical plane, it is called the plunging, and this is the pitching. So these motions are called the longitudinal equation of longitudinal motions, and these motions we are only going to take one motion, that is the only pitching. This is only possible when we are fixing our model in wind tunnel. So pitch is basically a motion which takes place on the lateral axis or y-axis. So in this, nose moves up or down in xz plane. So this is the x plane, and so in this plane. So this is the plane. So this is the x and this is the z. So any motion either in x direction or in this z direction or this one rotation. So two linear motion, that is in the x direction in the this, or and one is in z direction, another is in xz plane, and this is the rotation, and the only one rotation, that is the pitching rotation, we are undertaking in this case. So in our previous classes we have discussed in detail that the lift coefficient is the function of, here this we can see CL is equal to F, the function of alpha dot Q and delta E, where alpha is the angle of attack and it is a angular change of angle of attack, it is a rate of angle of attack, Q is a pitching rate, and delta E is a deflection of elevator. Same way, we know that Cm is equal to Cl into Lt. So Cm is also function of Cl, and this is the function of, again, function of alpha dot Q and delta E. So this coefficient of moment is also the function of alpha dot, this is alpha dot Q and delta E. I think alpha dot, you know, angle of attack, this alpha is angle of attack, alpha dot is rate of change of angle of attack, and Q is a pitch rate, and delta E is a pitching, and this is delta E is elevator deflection. So this you can see what is the delta E, this is the tail plane, and this is the your elevator, this is your hinge point, and if we deflect this is called from here horizontal to this axis, this angle is called the delta E deflection, and this is called elevator deflection. Okay, so all the points, I think it is clear now. Now I am going to discuss about pure pitching. Pure pitching, we can write the coefficient of moment as CL, and this CL is equal to CL naught plus CL alpha dot into alpha dot. This is, CL alpha into alpha plus CL dot into alpha dot C bar by 2U1 plus CL delta E into delta E. We have made here alpha dot C bar by 2U1. We have made this alpha dot as a non-dimensional form. So this will be alpha dot C bar by 2U1. So this we have taken here, and CL delta E into delta E. Here if you take the coefficient of moment, this coefficient of moment is equal to Cm naught plus Cm alpha into alpha plus Cm dot into alpha dot C bar by 2U1 plus Cm delta E into delta E. Now we have to see that pure pitching means. What is the meaning of pure pitching? That we have to understand, and here we have to take some approximation to solve the problems. To make the differential equations in an algebraic equation, we have to do some mathematical manipulations, and these manipulations are undertaken here and made some approximation. This we can see here. So pure pitching means only theta pitch angle is varying with no plunging allowed. So what is the plunging? If aircraft is flying like this and there is some disturbance and it is moved like this, so this theta is increased. Due to increase in the theta, there is angle of attack is also increased. So lift will be in upward direction. Aircraft will start moving like this. In pure pitching case, we are not, and this going up and down is called the plunging. This plunging is not permitted in this given pure pitching condition. So in the real aircraft, pure pitching is not possible. However, if you do this wind tunnel experiment on the aircraft, we can find out and we can get the result very accurately, and these results are quite matching, and we can find out by this help the natural frequency and the damping ratio, and by these two parameters we can assess that whether the aircraft is stable, aircraft is dynamically stable, or aircraft is dynamically unstable, or aircraft is neutral stable. That we are going to find out by the very simple approximation by the help of the pure pitching condition. So you can see here that one aircraft is there. In this aircraft, if you can see, this is the horizontal plane. This is the horizontal plane, that is the XY, and the velocity of this aircraft, this is the relative velocity V. Okay. So this is the flight path angle gamma. Gamma is flight path angle, and from here to here, this one is the angle of attack alpha. This is called angle of attack is alpha, and from horizontal to this axis of the aircraft, this is the axis of the aircraft. This is angle is called the theta, and this theta is called the pitch angle. This theta is called pitch angle. Okay, so these are the I have explained about the gamma. Gamma is a flight path angle. It is the angle between the relative velocity and the horizontal plane. Angle of attack alpha is defined as the angle between the relative velocity and the x-axis of the aircraft. Theta is a pitching angle. This is the angle between the x-axis of the aircraft and the horizontal plane of the aircraft. So these three, and here we can see that by this diagram, theta is equal to summation of the flight path angle gamma plus angle of attack alpha. So I am writing here, it is a flight path angle gamma plus angle of attack alpha. Okay, so this theta, and theta is equal to what? It is a pitch angle. So this pitch angle theta is equal to gamma plus alpha. For the pure pitching case, we can see here in this, if this is the wind tunnel, we have fixed the aircraft from the bottom. This is your mounting. Aircraft is fixed. The wind direction V infinity flowing for here. Here if you see, there is no gamma. Gamma is 0. So in this case, if the gamma is equal to 0, this pitch angle will be alpha is equal to angle of attack. So whatever you are giving this alpha will be also equal to the theta. So here theta is equal to alpha if gamma in wind tunnel. We can see here that in wind tunnel this case is possible. So theta is equal to alpha when gamma is equal to 0. Now pitch rate theta dot is equal to q. It is also pitch rate, and this is approximated as a alpha dot in tunnel. In pure pitch, if theta is equal to alpha and when gamma is equal to 0, this case is very well possible. Now we are trying to find out a natural frequency. Okay, because to have the dynamic stability, we should know the omega n and damping ratio zeta, and trying to simplify this equation. So we have taken that wing is the symmetric, so Cm naught is equal to 0. You know that for this symmetric wing at 0 degree angle of attack at alpha is equal to 0, Cm will be 0 for the symmetric case. So we have taken for the simplicity that wing is symmetric wing, and we know that moment equation is equal to Iyy and q dot. This we have derived, I think you remember in our previous classes. For the pure pitching case, the moment of the aircraft is equal to Iyy. It is a moment of inertia with respect to the y axis, and this is the pitch rate. This is the q dot. Now Iyy into q dot, we know that pitching is equal to force into distance. So half rho v square as force into c bar, then Cm alpha into alpha plus Cm alpha dot into alpha dot c by 2u plus Cm q c bar by 2u plus Cm delta E into delta E. You know why we have made this? This we want to make that alpha dot and q dot to non-dimensional form. If you want to make, then only this, otherwise alpha dot and q, they are not non-dimensional form. But in this equation, we want Cm in non-dimensional form. To have the non-dimensional, we have made this term and this term, we have multiplied by c by 2u, here also c by 2u. If you multiply it, alpha dot will become non-dimensional. So that is the purpose of multiplying alpha dot c by 2u1. So now, if you want to find out q dot, so q dot is equal to half rho v square s c bar by Iyy, and here Cm alpha into alpha plus Cm alpha dot into alpha dot c by 2u plus Cm q into q c bar by 2u plus Cm delta E into delta E. I think it is very much clear, simple mathematics. So now we will make further simplification. We will make half rho v square s c bar by Iyy Cm alpha. We will make as a m alpha, and half rho v square s c bar by Iyy into Cm alpha, we will make the m alpha dot. Like this, we will make for this term, we will make the mq, and for this term, we will make m delta E into delta E, where m alpha is equal to what? Half rho v square s c bar Iyy into Cm alpha. m alpha dot is equal to half rho v square s Iyy c by 2u into cm alpha, and mq is equal to half rho v square s Iyy c bar by 2u cmq. So here m alpha dot mq are the dimensional derivatives. However, if you take the cm is not the dimensional, it is a non-dimensional derivative. Okay, so this is the difference between this equation and the previous equations. So now the cmq is a non-dimensional derivative. In pure pitching motion, theta degree of freedom is only given, velocity remains constant. Now, using the Laplace transformation in this equation, that is q dot is equal to m alpha into alpha plus m alpha dot into alpha dot plus mq into q m delta e into delta e. So we will transform with the Laplace transformation, and this equation is a differential equation. This differential equation, to solve this equation, we have to convert into algebraic equation, and these algebraic equations can be solved with a very simple algebra by quadratic equations. So the objective of Laplace transformation is to solve this differential equation to the algebraic equation. So now here SQS is equal to m alpha into alpha s plus m alpha dot into s into alpha s plus mq into qs plus m delta e into delta es. We know that here q is equal to theta dot. Previously we have given that q is equal to theta dot, and we know for the pure pitching theta is equal to alpha if we are putting in the wind tunnel here. So here if the gamma is equal to 0, theta is equal to alpha. So this gamma dot is equal to 0. So this theta is equal to alpha dot. So here q is equal to alpha dot is equal to q dot, and this is the alpha dot. So here qs is equal to s theta s. Okay, so in place of here in this qs we can write s theta s, and here also in the alpha term we can write s into alpha s. So this we will be putting in this equation number 8 here. For the q we will put s alpha s. So we can get here that SQS is equal to m alpha into alpha s plus m alpha dot into s alpha s plus mq qs plus m delta e into delta es. We know that qs is equal to s alpha s. So from equation we will put here for qs we will put s into delta s. So it will become s square alpha in s m alpha into alpha of s plus m alpha dot s alpha into s plus mqs alpha s plus m delta e into delta es. Now we can see here that alpha s is equal to s square minus, you just see here all alpha, if we take one, this alpha, this alpha, this alpha, if we take one side and alpha s we will take the common, so here s square minus mq plus m alpha dot, okay, into s, because both are having this s, okay, so s minus m alpha is equal to m delta e into delta es. So now alpha s by m delta e, or this delta e s is equal to m delta e divided by s square minus mq plus m alpha dot s minus m alpha. So now we have to transformation function, and now we got here, this is the characteristic equation, and this characteristic equation we have to solve. So here we got the characteristic equation s square minus mq plus m alpha dot s minus m alpha is equal to 0. So this equation we got. Now we have to solve this problem. Now this we have to compare this equation with standard equation, that s square plus 2 zeta omega ns plus omega square n is equal to 0. So here, if we compare from the previous equation, so omega square n is equal to minus m alpha. So omega n is equal to under root minus m alpha. And if we compare 2 zeta wn, so this will be minus mq plus ma alpha. So here this zeta is equal to what? Minus mq plus ma alpha divided by 2 under root minus m alpha, and this is the omega n. This is the value of omega n. So 2 into omega n. Here, if you see that, what is the m alpha? It is visible that under root minus m alpha we will get the imaginary values, but it is not so, because m alpha is itself is a negative. So it is half rho v square s cm alpha by Iyy. So this cm alpha, if you see for the static stability case, this cm alpha should be negative. So this negative and this negative, it will become the positive. So cm alpha is negative, or minus cm minus m alpha will be positive. So the value of equation C here, this will be positive, not a negative. Okay, so this from here we can find out the omega n, and we can also find out this zeta. So this omega n and zeta, by this we can get so we have made an attempt to find the natural frequency omega n and damping ratio for the pure pitching case. Pure pitching case, equation B and C gives the value. So this equation here, equation number B here, this is the equation number B, this equation and this C equation. So we got the omega n and zeta we have found out. So by this we can find out the aircraft is stable or unstable, or it is a short time or the long time, short period or the long period, this motion we can very well find out. So now I have to go further. The aircraft dynamics is the one of the most important behavior of the airplane. Aircraft being statically stable, not have the dynamic stability of the airplane. We should study the dynamic behavior, and we have already developed the longitudinal perturbed equation of motion. By now, you know that this u dot is equal to plus fx, w dot is equal to plus fz, and q dot is equal to plus m. So we find the dimensionless equation of motion as A matrix into x is equal to b, and we got characteristic equation like as to the power 4 plus bs to the power 3 plus cs square plus ds plus e is equal to 0. So we will get the fourth order of equation, and we can see that a, b, c, d, e, a, b, c, d, e, this all should be greater than 0. We are talking about the Routh criteria and how we can find out. So a, b, c, d, e all should be greater than 0. The second condition is d into bc minus a minus b square e also should be greater than 0. And this Routh criteria is e should be the last term. It should be greater than 0. So we got important relation in the previous classes that cmu, it is the derivative, it is a dcm by du. So this is equal to m1, it is a m1 dcm by dm. It should be less than 0 for subsonic case. So for the subsonic case, the variation should be less than 0, and for the supersonic case, it should be greater than 0. So if we draw the Cm versus U, so mostly it will be like this, then it will go like this. So here it is a M 0.6 and this will be 1, M1. So if it is a Mach 1 case, this is a supersonic case, it will be greater than 1. It means it will go upward. So for the high speed aircraft, we have done the equation and solved in the previous classes. As long as real part is negative, the attitude will decay, that is e to the power real term is less than 0 as decay the real part. Just you can see here, above is this right side is the imaginary part and this is the real part. So by solving this, if your roots are in the left side of this, then it is decaying and it is a stable case. Stable case. This we can find out by this, and it gives a very good result. Now, second order system, that is the mass spring damper. Second order system is called the mass spring damper system equations. In this, m d2x by dt square plus c dx by dt plus kx is equal to ft. So now the characteristic equation is given by lambda square plus c by m lambda plus k by m is equal to 0. Solving this second order equation, we will get lambda 1 2 is equal to minus c by 2m plus minus under root c by 2 m square minus k by m. If here this c by 2m is greater than under root km, then roots are negative and the real. So if we are getting this c by 2m greater than under root k by m, then roots are the negative and real. And if c by 2m is less than km, then they are the complex conjugate roots. And if c by 2m is equal to k by m, then only we will get lambda 1 and 2 is equal to minus c by 2m. So this is called the critical damping time required smaller to come to the equilibrium condition. So these parameters we have to understand very much clearly. So solution for this case will be x is equal to c1 plus c2t e to the power lambda t. So here if you see now how to handle the second order equation. So x double dot plus c by m x dot plus k by m x is equal to ft. So natural frequency omega n, we know under root k by m, and the damping ratio zeta is equal to c by 2 under root km. So now differentiating this frequency omega n, damped frequency omega n is equal to under root km minus c by 2m whole square. So we can write the second order equation as x double dot plus 2 zeta omega n x dot plus omega n square x is equal to 0. Now we can use the Laplace transformation and we can solve this equations. We know that if x is equal to e to the power lambda t, so dx by dt is equal to lambda e to the power lambda t, and d2x by dt square is equal to lambda square e to the power lambda t. So these are the very simple differential equations are given here. Now if we make the Laplace transformation of this equation, we can get s square xs plus 2 zeta omega ns xs plus omega square n xs is equal to 0. So if we take the xs common, so we will get here s square plus 2 zeta omega ns plus omega square n is equal to 0. So this equation is a characteristic equation. So s square plus 2 zeta omega ns plus omega square n is equal to 0. Let's see with some previous example. If we have lambda 1, 2, because if you solve this, you will get two conjugate equations, and here if you see lambda 1, 2 is equal to minus 1.008 plus minus j 2.651. Another root you will get lambda 3 and 4 roots minus 0.0069 plus minus j 0.0905. If you plot this equation, this you can see here that this is a minus side, so it is a 1.008 here. Okay, and here if you see this is also minus, but it is a 0.069, very less. It is here only. So this, and if you see this here, it is a 2.651 plus and 2.651 minus. For this equation, it is here. And if you see this equation, they are here. So the roots can be displayed graphically as shown in the plot with the positive and the negative roots of the given problem. So here this is the real axis and this is the imaginary axis. Okay, so these all parameters are available, and if you plot, if all are there towards the left side, this, then it is a stable case. So here if you see that s square minus sum of the root into s plus product of the root is equal to 0. So we have given some numbers, s square minus 1.008 minus 1.008 s plus product of the root minus 1.00 square plus 2.651 square is equal to 0. So if here we will get s square plus 2.0165 plus 8 is equal to 0. We got this equation. Now, so here if we compare 2 zeta omega n is equal to this value 2.6165 and omega n square is equal to 8. So omega n is equal to 2.863 radian per second, and if I put this value here, I will get zeta is equal to 0.355. For long period or the Phugoid mode, the kinetic energy will change to the potential energy and potential energy will change to the kinetic energy, but alpha will remain constant. So here lambda 34 will give omega n is equal to 0.019 radian per second and zeta 34 will get 0.076. So this you can see lot of difference is there. Here damping is also very less and the frequency, natural frequency is also very less. So this is a high damp, so called the Phugoid mode. So this is the Phugoid mode and this is the short, because damping is very high. So if you disturb here, it is just go like this immediately. But in this case, if you like this, it will go like this slowly. This is called the Phugoid. Okay, and this is the short period. Okay, so if you see here, what is the short period? If it is disturbed, it is like this. It is short period. In that, omega n is high and zeta is also high. But in the Phugoid mode, it is going like this, slowly. After some time, maybe 5 seconds or 10 seconds, it will come. But in the short period, within fraction of second, it will vibrate and it will come to its equilibrium position. So that is the difference between these two conditions. Now, short period approximation, we have to see the short period approximation. We try to understand the equation in the form as to the power 4 bs cube plus cs square plus ds is equal to 0. So we got here lambda 1, 2 is equal to minus 1.008 plus minus j 2.651 and another roots lambda 3, 4 we got minus 0.0069 plus minus j 0.0905. So in this we have the second order of equation. We get the root lambda 1, 2 and lambda 3, 4. These roots are complex and the conjugate, so it's oscillatory nature. So this will be oscillating. This you can see here in this diagram. This is oscillating like this. They are oscillating like this, so if you all peaks, if you touch, you will get like this, and E, this is the value of E. And if you are disturbing here, it will go like this, it will stop. But in the long period, or it is called phugoid. In the phugoid case, if you disturb, it will go, and slowly it will take sufficient time, and after some time it will come to its equilibrium position. Now some mathematical expression for the short period approximation is needed, explained in the next slide. So this we have already discussed earlier, so we need not to do much about these all things. And Phugoid mode, we can see here, this is the equation for the, and we got here this equation, s square minus xus minus zu by u1 into z. And from here, we can find out the root to calculate these values. Okay, so like this, we can see here that the zeta value is 1 by CL, 1 by CLD. And so CL by CD is very important here also to find the damping will be least. If CL by CD is more here, the damping will be least. So if more CL by CD, it is less stable case. Okay, so here we have the one numerical. So it dx by dt plus 2x is equal to 0, and condition is given x0 is equal to 1. So we can do the solution here, that dx by dt, we can write px plus 2x is equal to 0. We have taken here x as a common, so p plus 2x is equal to 0. So p plus 2 is equal to 0, plus 2 is equal to 0, so p is equal to minus 2. So we can write that x t is equal to c1 e to the power minus 2t. Using the initial condition, x is equal to 0 is equal to 1. So we got the c1 is equal to 1 and xt is equal to e to the power minus 2t. So this is the solution for this problem. Okay, so I have taken this references, Robert C. Nelson, Aircraft Stability and Control, and I have also used the NPTEL lecture for Aircraft Stability and Control by Professor A.K. Ghosh, and these are the links for that. Thank you very much for joining. I will be taking the next lecture with more detail about some numericals. Please be tuned. My email is ydwivedi@gmail.com. You are welcome to ask any question in this. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.